In this lesson, we will examine a type of notation that allows us to express familiar concepts in a different way. Now, in the past, we have examined expressions like the one shown here. Notice that the value of this expression depends on the value of x. So, for example, if we want to find the value of this expression when x equals 3, we take the expression and plug in 3 for x. When we evaluate this, we get 16. So this expression has a value of 16 when x equals 3. We can express the same concept here using function notation. Now please note that this notation here does not mean f times x. It is just the notation we use to define a function. Now with this notation we are saying that 2x squared plus x minus 5 is a function, and its value depends on the value of x. This is the same as saying 2x squared plus x minus 5 is an expression whose value depends on the value of x. Now with this new notation, we say f of x is equal to 2x squared plus x minus 5. You can think of this as taking the expression 2x squared plus x minus 5 and assigning it the name f. So if we want to find the value of 2x squared plus x minus 5, when x equals 3, we use this notation. We read this as follows. If f of x equals 2x squared plus x minus 5, then f of 3 equals what? So we'll take our function here, and to find the value of f of 3, we'll plug 3 in for x. At this point, when we simplify, we get 16. So if f of x equals 2x squared plus x minus 5, then f of 3 is equal to 16. Notice that we are simply using different notation here to express the same concepts that are expressed here. Okay, now here's an example of a word problem that we can rewrite using function notation. The cost C of a taxi ride is given by C equals 1.5 m plus 2.5, where m is the number of miles driven. Notice that the cost of the ride depends on m, the number of miles driven. So if we want to find the cost of a 4-mile trip, we must recognize that m equals 4, and we want to find the value of c when m equals 4. To determine this cost, we'll replace m with 4 to get the following. When we simplify this, we get 8.5. So the total cost of a 4-mile trip is $8.50. Now another way to express this information is to say that we have a function c that helps us determine the cost of a taxi ride. So here, c of x is equal to 1.5x plus 2.5, where x is the number of miles driven. If we want to find the cost of a 4-mile trip, then we want to find the value of c of 4. In other words, we want to find the value of the function c when x equals 4. To find the value of c of 4, we will replace x with 4 and evaluate this to get $8.50. So once again, we are simply using different notation to express the same idea. So if we are told that f of x is equal to x cubed plus 5x minus 1, then we can evaluate f of 2 by plugging 2 into the right-hand side. When we simplify this, we get 17. So our function f evaluates to be 17 when x equals 2. In other words, f of 2 equals 17. In this example, if we want to evaluate f of negative 1, then we plug negative 1 into our function to see that f of negative 1 equals negative 7. In this example, we want to evaluate f of k. To do so, we'll plug k into our function. At this point, we cannot simplify the right-hand side any further, so we can say that f of k is equal to k cubed plus 5k minus 1. Finally, in this example, we want to evaluate f of 2m. We will do this by plugging 2m into our function. When we simplify the right-hand side here, we see that f of 2m is equal to 8m cubed plus 10m minus 1. Okay, let's summarize. The important takeaway here is that function notation is really just a different way to express the concept of evaluating expressions. In this lesson, we will learn how to solve equations involving absolute values. Now, the absolute value of a number, say x, is expressed using this notation, and it can be defined in more than one way. One way is to say that the absolute value of x is equal to x if x is greater than or equal to 0, and the absolute value of x is equal to negative x if x is less than 0. So the absolute value of 7 is 7, and the absolute value of negative 3 is 3, and the absolute value of 0 is 0. Another way to define the absolute value of a number is to say that it is the number's distance from 0 on the number line. So, for example, to determine the absolute value of negative 4, we notice that negative 4 is 4 units away from 0 on the number line. As such, the absolute value of negative 4 is equal to 4. Okay, now let's make some observations about equations involving absolute values. For example, if the absolute value of x is equal to 4, then we know that x must equal either 4 or negative 4. Similarly, if the absolute value of x equals 11, then x can equal either 11 or negative 11. In general, if the absolute value of x equals a, where a is greater than or equal to 0, then x must equal either a or negative a. Okay, now let's use this property to solve the following equation. If the absolute value of x equals 3x minus 4, then we can apply our rule to see that x equals 3x minus 4, or x equals negative 3x minus 4. At this point, we have two equations to solve, x equals 3x minus 4, or x equals negative 3x minus 4. We'll begin with the first equation. To solve for x, we can subtract 3x from both sides, and then divide both sides by negative 2 to get x equals 2. To solve the next equation, we'll first expand the right-hand side, then add 3x to both sides, and then divide both sides by 4 to get x equals 1. So it appears that this equation has two possible solutions. However, when we solve equations involving absolute values, it is possible to get solutions that do not satisfy the original equation. These are called extraneous roots, and we must be sure to check each solution to confirm that it satisfies the original equation. So first we'll check the solution x equals 2 by taking the original equation and replacing x with 2. When we simplify the right-hand side, we get the absolute value of 2 is equal to 2, which is true. So x equals 2 is a valid solution. Now let's check the solution x equals 1 by taking the original equation and replacing x with 1. When we simplify the right-hand side here, we get the absolute value of 1 is equal to negative 1. Since the absolute value of a number can never be negative, x equals 1 is an extraneous root, which means the original equation has only one valid solution. That is, x equals 2. Okay, let's summarize. To solve most equations involving absolute values, first apply the following rule. Then solve the resulting equations, and finally be sure to check for extraneous roots.